Hello, in this video we're going to be talking about minimization of Boolean expressions. In the past we used Boolean properties to minimize certain Boolean expressions, but in this video we're going to see a different method. The first one is going to be Karnaugh map and the next one will be Quinn-McCluskey procedure. The difference is that when you have more than 4 input like x1, x2, x3, x4, more than that you have x5 and x6, you cannot use this Karnaugh map. And Karnaugh is after the name of the person that did discover this method. So it's more than 4 input, you cannot use Karnaugh map. You have to use another procedure called Quinn-McCluskey procedure. So, and sometimes it depends, as we say here, if the network is to build only once, you don't need to spend time thinking of minimization. But if it's going to be mass produced, then it is worth minimizing the Boolean expression. So this way the cost will be less for the network connections or gates. Here is how the method, you could read all the expressions, but I'm going to get into an example. So when you have a truth function like this one, so you have a 1 here and a 1 here. So this one meaning I have x1, x2, and right here you have x1 not, because of the 0, x1 is not, and then x2. Well, this K-map, that means you have only 2 inputs, so that means I must put it in a square, 2 by 2. And then you have x1, x1 not here, and x2, x2 not here. This is very important, the order x1, x1 not here, x2, x2 not. And then you put whatever you have from this table. What I have is x1, x2, here is x1, here is x2, so I have a 1 here. And then I have x1 not, x2, that means I have a 1 here. So this is how I take information from the truth function to this map or these squares. Because as I said, 2 by 2 is enough because you have 2 inputs. 2 by 2 square. And then it comes to grouping. Then you group it this way because they are adjacent. And you look up. And because x1 varies, you go from x1 to x1 not. It's going to cancel. And all what's left is x2. So basically, if I have x1, x2 plus x1 not x2, and I did all those properties as we did before, I'm going to use commutative property first, and then I do the distribution property next, and then this is a 1, so it's going to give me identity, which is just x2. So all this work can be saved by looking at the map and looking up. And what's the most important thing? How you set up the map, the ordering of this x1, x1 not, and I'm going to go over it over and over until you get that. So what's important is the ordering of the map and the grouping. And we'll get to those examples. Again, what I'm talking about, feel free to read everything here in these notes. And we'll go to, if I have 3 inputs, x1, x2, x3, what do? This is how you set up the map, or do you set up the table? x1, x2, x1, x2 not, x1 not, x2 not, x1 not, x2. You may think it's hard to remember, but remember, I need, in this side, I will put x1, x2, and down this column is going to be x3. But for these 2 variables, x1, x2, remember, 1, 1, 1, 0, 0, 0, 0, 1. It's always you share a 0 when you jump from one column to the other. You share a 1 or you share a 0. So you could remember 1, 1, 1, 0, 0, 0, 0, 1. That's very important to set it up this way. So the same if you have 4, and as I said, K-map works only when up to 4 inputs. So you have x1, x2, x3, x4. And so as you see, for x1, x2 varies this way. 1, 1, 1, 0, 0, 0, 0, 1. The same with x3, x4 goes 1, 1, 1, 0, 0, 0, 0, 1. 0 means negation, and 1 it's not negated. That's how we did it before. So if you read here, the rightmost square in a row are adjacent. They differ by exactly one variable. And also the top and the bottom square in the column are adjacent. So that's what I mean by 1, 1. So like this one here and this one here, 0 here and 0 here. That's what I mean, adjacent. So that's number 1. It's important to know how you set up the table. And then whatever variables you have, you put them as ones, you read them in the table, and then we're going to minimize. We're going to group. But how do we group things? Here is how we group things. So if you have 3 inputs like this one here, you have 8 squares, because 2 to the power of 3, 8 variation. So assume we have this here represent this table here. This is going to be x1, x2, not x3. So as you see, if it was given to me like this is not minimized. So I take these variables and I put them in a table. The table must be set this way. x1, x2 here and x3 here. And then x1, x2 not, x3. This is this one here, the first one. Then x1 not, x2 not, x3, x1 not, x2 not, x is this one here. Third one is here, and that fourth one is here. So you put them on this table, and then as I said, we're going to group them. How do you group them? You always group groups of 2, 4, or 8. Always groups. You look for groups of 2 ones, 4. So look for 2, 4, and 8. You don't go with the groups of 3 that are adjacent. So for example, when they are adjacent to each other, you could group them this way. When they are like this, because you think of this like a piece of paper that can be folded this way and this way, so this one can be grouped with this one here. Or the same way this paper can be grouped this way, or can be grouped this way. You fold the paper each on the edges, and then this will be grouped with this. And let's see, how do we minimize it? You make groups of 2, 4, or 8, and the group, that means the ones must be adjacent to each other. So either they can be adjacent just like this, or they can be adjacent by folding the paper, like here and here, okay? This is how we group things. Or you could have a group of 4 of ones all adjacent to each other like this one. This one is group of 4 as well. Why? Because this paper again can be folded this way, like a tube when you make the whole paper fold. And then the same way this group of 4. Or sometimes we could take all corners together, or you could pull them here all together. I'm talking about piece of paper like you fold in all corners and you have one thing. Or you could have a group of 8, meaning this 4 and this 4. Or group of 8 either here or here. These are the possibilities, how you group things. But what does it mean, this grouping? How do we reduce this thing? Let's see. So I'm going to just change my color. This group here, I'm going to write it in blue. So you look up at the group. Once you group them, you look up. You see that x1 differs from x1 to x1 not. That means it's going to cancel, okay? What's left? x2 not and x3. x2 not and x3. Similarly, I'm going to change my color. This group, you look up, and what's changing? x1 again changes from x1 to x1 not. They're going to cancel. And what's left is x2 and x3 not. And that's how we go from this expression reduced to this one here. So similarly, let's do the next example. I want to think of this group here. This is one group of 2. So on the top, there is only one thing in common, which is x1, x2 not. But right here, if you look this way, what changes? x3 not changes. So what's left is x1, x2 naught, x4. And the other group here, this group of 2, again you're gonna look up and I see x1 changing, but what's left is x2. And horizontally we still have x3 naught, x4 naught. So this expression will become as follows: x1, x2 naught, x4 plus x2, x3 naught, x4. So we get reduced to this expression. So the same here, this group of 4. If I look horizontally, x3 is gone. And if I look vertically, x2 is gone. So what's left? x1. So the whole group get reduced to just x1. Again, this example, I group this way. 4, I have a group of 4. So x3 cancel out because I go from x3 to x3 naught. If you look vertically, I see that x1 varies. x1 to x1 naught varies, so what's left is just x2. Similarly, this one here, this group 4 with this group 4. So look vertically, what's going to change? What's changing is x1. What's left is x2 naught. Then you look horizontally and see what's changing is x3 naught, and then x4 stays. So the whole thing becomes this expression. The next one here, I group them by the corners, gives me 4. Then I look up, I see that x1 is changing, what's left is x2. And if you look horizontally, I mean this way, I see that x3 is gone, but x4 stays. And that's the expression for this one here. How about this one here? This C, when you have 8. So if you look horizontally, I see that x3 varies, x4 last, okay? And if I look vertically, I see that x2 varies, also x1 varies. So the whole thing become just x4. When you have 8 within 16, it's just one input. When all 4 inputs become just one output, which is just the x4. And right here, again, if you look horizontally, I see that all of them varies, all. But if I look vertically, x2 varies. We go from x2 naught to x2, but x1 naught stays. So the whole thing gets reduced to just x1 naught, or minimized to x1 naught. In the next video, we're gonna go over just examples of the K-map. I hope this is helpful.